So, this would be a tutorial class based on the concept that we have covered in the previous class, which is the temperature profiles and special considerations for systems which have some heat generation capability in them. And we have seen that it's the temperature profile in most cases should be parabolic. It's going to be symmetric parabola if both sides of the plane wall they are maintained at a constant temperature, and the mid plane at x equals 0 is going to be the plane with maximum temperature. In the mathematical requirement of that plane, the temperature being maximum at that plane would require that that plane is going to be an adiabatic plane. So, the first case I will draw your attention to the figure that I have over here. So, this is a material A, a plane system of material A of thickness 50 millimeter, and then on the other side of A I have another material B whose thickness is 20 millimeter. The one side of A is insulated, that means at x equals 0 you have insulation. The temperature at this point is denoted by T0. The temperature at the interface between A and B is T1, and on the other side of B I have a liquid whose temperature far from the wall is T infinity, and the liquid is flowing along the plane along this B, while so its temperature is at 30 degree centigrade, and this flow creates a convective heat transfer coefficient of 1000 watt per meter square per Kelvin. So, I hope the picture is clear to you. A wall which generates heat sandwiched between an insulated surface and another plane, another wall of different thermal conductivity, but without any heat generation. Wall B on the other side is exposed to a convection environment where the temperature and the H are provided. The thicknesses are different, and if you look at the material A, the wall A, it has a thermal conductivity of 75, and the amount of heat generation in this case is going to be 1.5 into 10 to the power 6 watt per meter cube. And when we consider the wall B, it does not generate, it has no heat generation capability. However, the thermal conductivity of this is twice that of A. So, what is required are, the first part is sketch the temperature profile under steady state, and we would also assume that T is a function of x only. So, if that is the sketch, we first need to find out what is the what does the temperature profile look like. So, it is a sketch, no numerical values are required, we just need to see the form, how does the temperature profile would look like. So, let us first consider the wall A. The wall A on one side is insulated, and on the other side its temperature, the junction temperature between A and B is known, and we are calling it as T1. So, if on one side of a plane wall the temperature is known, the other side is perfectly insulated, and in this wall if heat is generated, then from our previous study we know that the temperature profile is going to be that of an inverted parabola. In fact, it is going to be half of an inverted parabola. So, that is how it would look like in the material A where there is heat generation. So, the temperature profile in this would probably look something like this, where it is half of a parabola with the apex is at x equal to 0. So, this is T0 and this is T1. When I come to material B, it's the T1 is known, the T2, which is the interface temperature between the material and the fluid, if T2 is known, and since Q dot is 0. So, in this specific case Q dot is not equal to 0, and in this case Q dot is equal to 0. So, what you are going to get is it is a case of two temperatures known with no heat generation. So, your governing equation would simply be d2T. So, the governing equation for this case would be d2T by dx square equals 0. So, if d2T dx square equals 0, then the temperature profile, as we have seen before, is going to be linear. So, this is what it should look like, in the temperature profile should look like at material B, and obviously there is continuity between. So, T1 on the A side of the interface must be equal to T on the B side of the interface, but from this point onwards it is going to be linear. And of course, the value of thermal conductivity would also tell us the gradient of this line. Higher the value of thermal conductivity, lower would be the slope of this line. So, if you did not have Q dot present in material A, you only have Ka and Kb to consider, then the slope of the temperature profile for material A would be more as compared to Kb. So, a system of higher thermal conductivity simply tells you that you require only a small delta T to conduct the same amount of heat. So, looking at the temperature profile at steady state between different surfaces, you would be able to say which one is of higher thermal conductivity and which is of lower thermal conductivity. So, the point so far is that it's in A it is going to be half of a parabola, inverted parabola, and in B it is going to be linear. Then the question still remains is, how would the temperature T2 which is at the interface between the material B and the liquid change from T2 to T infinity. Again I reiterate that there would be the formation of a boundary layer close to the surface of the solid which is in contact with the liquid. So, due to the formation of the boundary layer, the temperature would change from T2 to that of T infinity in a region which is quite thin, and that is the concept of thermal boundary layer. The same way we had the momentum boundary layer. So, this change in temperature from T2 to T infinity will be very sharp over a thin region, and then it is going to asymptotically reach the value of T2. So, the profile would look something like this, and this is your T infinity. So, this is the boundary layer in which the temperature is going to change, and you would be able to see what is how the temperature profile look like in this case. So, the salient features of the temperature profile are that it's inverted parabola, in A. In B, it is simply going to be a straight line, and from B to liquid it is a sharp change due to the presence of the thermal boundary layer. Sharp change, and then gradually it will go to T infinity. The part B of this problem tells us that we need to find out, the part 2 is to find out T0 of the insulated surface and T2 of the cooled surface. So, this is the one. So, this is A, B, and you have a liquid in here. So, this is your T 0 and this is your T 2. All the numbers which are provided to you. So, you have to find out what is going to be the T 0 of the insulated surface and T 2 of the insulated of the cooled surface. Now, it is probably easier if you find out T 2 first and then go for T 0. Why so? Because you have some amount of heat which is generated in A, but there is no heat which is generated in B. So, in order when steady state will reach, then what you would see is that all the heat which is generated in A has to travel to the right of the figure all the way to the liquid, because one side of A at x equals 0 is perfectly insulated. So, no heat can cross from A to the outside, all the heat has to travel inward through B to the liquid. So, if I end the heat flow from A through B up to the interface of the solid and liquid is going to be a process, it is going to be by conduction. Beyond that plane, beyond that fluid solid interface, the heat is going to be transported by convection. So, if we can find out what is the total amount of heat generated in the system and equate that with H A delta T, which is Newton's law of cooling, and this delta T is simply going to be T s minus T infinity. So, that is going to be the equation which one should use in order to find what is the heat, what is the temperature, unknown temperature T 2, because T infinity is known to me. So, let us write that and see what we get out of this. So, H times area times T 2 minus T infinity, this is the heat which is moving in this direction by Newton's law of cooling, must be equal to the amount of heat generated per unit volume times L times A, and this length obviously will have to be L A. So, this is L A and what we have here is L B. So, this is the equality of heat generation inside and all the heat being convected out at that point. So, A will cancel and what you would get is that T 2 is equal to T infinity plus Q dot L A by H, which when you put the values at 30 plus 1.5 into 10 to the power 6 into 0.05, because this is 50 millimeters, divided by H is 1000 watt per meter square Kelvin. So, your T 2 would turn out to be 105 degree centigrade. So, that is going to be the temperature at this point. Now comes the second part, how to evaluate the temperature T 0 over here. Now, when you if you write the governing equation for A, so for material A, the governing equation would be d 2 t by dx square plus q dot by A is equal to 0 at steady state. So, this would give you dt dx as minus q dot x by k, and this is of material A plus C 1, and I use the first boundary condition. So, C 1 is the integration constant. I use the first boundary condition B C 1, which tells me something about what is going to be the value of slope at x equals 0. The value of slope dt dx at x equals 0. So, dt dx at x equals 0 must be 0, since this is an insulated surface, since x equals 0 is an insulated surface. So, this simply tells me that C 1 is going to be equal to 0. So, that is one of the integration constants automatically taken care of. So, I integrate this once again. So, the temperature, which is a function of x, would simply be minus q dot x square by 2 k a plus C 2, where C 2 is the other integration constant. So, T at x equals L A, that means at this point the temperature we know that the temperature is T 1, and this should be equal to, this would give me C 2 is equals T 1 plus q dot L A square by 2 k A. So, this is my C 2, and therefore, T at x, finally, this is going to be q dot by 2 k A L A square minus x square plus T 1. So, this would be the temperature profile inside A in terms of T 1, which is the temperature over here, but my aim is to obtain T naught. I have to evaluate what is T naught. So, I get an expression of T in terms of T 1, which is yet to be evaluated. So, I am simply going to first put x equal to 0 in this expression, and the moment I put x equals 0, then T x is simply going to be equals T 0. So, T at x equals 0, from this previous expression T at x equals 0, I call it as T 0, which would be q dot by twice k A times L A square plus T 1. So, the previous equation, substituting x equals 0, my T at x equals 0 is T 0, x equals 0. So, this is what the form is going to be. But the problem still remains is, I do not know what is T 1. How do I find out T 1? T 1 is unknown to me. So, in order to find T 1, and I draw the profile once, I draw picture once again. So, this is A, B, and you have T infinity over here, and you have some q dot in this, but no q dot in here. So, the heat has to flow in this direction, the same heat will flow in this direction and also to the fluid. So, the temperature over here is T 1. So, the potential at this point is T 1, the potential at this point is T 2, and the potential at this point is T infinity. So, if I draw something like a thermal circuit, what I get is the temperature at this point is T 1, over here is T 2, and over here is T 3. In between T 1 and T 2, I have a conduction resistance. In between T 2 and T infinity, I have a convection resistance. So, what are these? These are R double prime conduction, and double prime simply tells its per unit area basis, and this is R double prime convection. So, for example, R double prime convection, the R convection is 1 by H A. So, R double prime convection is simply going to be 1 by H. So, that is going to be the convective resistance in between these 2 points. And what is the current or equivalent of current, which is heat which is flowing through it? That must be all the heat which is being generated in here, that is Q times A times L A. So, that is the heat which is flowing through these 2 resistances, and since I have expressed these 2 resistances in terms of per unit area basis, so I drop the area from here. So, this is the heat generation per unit length which flows from T 1 to T 3 through T 2. So, the same amount of heat flows to each one of them, and these 2 resistances obviously are in series. So, this heat which flows through this is Q dot times L A is equal to the potential difference T 1 minus sorry, this is T infinity, T1 minus T infinity divided by the sum of all resistances which R double prime conduction plus R double prime convection. So, this is T1 minus T infinity by LB KB plus 1 by H. Look carefully, what I have done here is the conduction resistance. What is the conduction resistance to heat flow? It is the conduction resistance that of B, because the amount of heat which reaches this plane is equal to Q dot times LA. So, this heat when it travels only because of a potential difference, and the overall potential difference is T1 minus T infinity, and the resistances it encounters are one conduction resistances and the convection resistance. The conduction resistance is due to the conduction resistance of B, which is LB by KB, and convection resistance is simply going to be 1 by H. So, when you plug in the values of L, LB, KB, H, T infinity and Q dot, LA, etc., what you are going to get is T1 as 115 degree centigrade. So, this is going to be the junction temperature, and what we have done over here is we have an expression for T0 in terms of T1, where Q, Ka and La are known to me. So, once I substitute T1 in this expression, Q dot La square by twice Ka plus T1, when I substitute this in here, putting in the values of Q dot etc., what you would get is T0 as 140 degree centigrade. So, this is a nice example, this problem is a nice example of how the concept of heat generation in a planar system can be applied when there is heat generation, when there is no heat generation, when you have conduction and convection both present in the system, and so on. So, I would urge you to solve problems like this from your textbook, and if you have any queries, then the TAs and I will try to answer them and clarify the concepts. I will just give you one more problem with answer for you to practice on based on the concept of again heat generation in planar systems. So, the problem that I am going to discuss, I am going to provide to you as a homework or as a problem for you to do at home is I have a system which is x, this is at x equals 0 and this is x equals L. This side is perfectly insulated, and the thermal conductivity of this is K, and you have some sort of a radiation which is falling on this surface, and the radiation is going to be absorbed by the material, and it is going to be absorbed by the material based on how close it is to the surface. So, obviously, when you are on the surface you get the maximum absorption, and as you move far away from this surface which is exposed to radiation, the amount that is absorbed is going to be less. So, the microwave radiation causes some sort of a heat generation which is obvious. So, this heat generation is going to be a function of x, where this is the x direction, and it is going to be Q0 times 1 minus x by L, where Q0 is just a constant, and let us assume that this wall, that the x equals 0 is maintained at a temperature T equals T0. So, the first part of the question is derive the differential equation for the temperature profile, and the second is solve with boundary conditions to obtain the profile. So, that is the problem. You have radiation which is incident on the wall. The radiation absorption has resulted in a volumetric source of heat generation, the functional form of which is given over here. This Q naught is a constant, and of course, it is going to be a decreasing function of x. So, starting with the problem, first find out what is the differential equation, and then use the appropriate boundary conditions to solve for the temperature profile. So, I suppose all of you would be able to see that the boundary condition is simply going to be d2t dx square plus q dot by x, q dot by k is 0. The only difference with the previous problem, the ones that we have discussed so far, is this q dot is not a constant, but it is a function of x. That is the only thing which you have to appreciate, which you have to realize for solving this problem. So, the variation of q dot, which is heat generated per unit volume, with x, the functional form is provided as q 0 times 1 minus x by L. So, if you look at over here, then the governing equation would simply be d2t dx square plus q naught by k times 1 minus x by L is 0. And what are the boundary conditions? The boundary conditions will remain the same, that at x equals 0, T is a temperature which is T is a temperature which is known to us, and at x equals L, that means at this point dt dx is 0, since it is an insulated wall. So, the governing equation is obtained in the same way, with the understanding that this q naught is a function of x now, and these are the two boundary conditions. So, you solve it on your own. I am simply going to give you the final form for you to check. So, the temperature profile here would be q naught by twice k times L square x by L this is going to be the temperature profile which you should get for such a case. I will give you one more problem very quickly. Again, you have to solve it on your own. So, I suppose you probably do not have any queries, but the only difference is this part where q naught is a function of x, rest are exactly the same. The third problem, tutorial problem, is you have a cylindrical heat source at the middle. So, this is a heat source at the middle, and the one that I have drawn over here. So, this is a tube. On the inside of the tube, I have a coating. So, on the inside of the tube, I have a coating, and this is just a radiant heater. And here I have a coating which is to be dried. So, this coating is to be cured by heating. Okay. And this is the cylindrical heater which is placed over here. The purpose of this heater is to provide a constant heat flux Q 1 double prime, constant heat flux Q 1 double prime to this. This is R1 from here to here, and from this point to this point is R2. So, this is the tube, this R2 minus R1 provides the tube wall thickness. The first part is find the temperature distribution in the tube wall. So, how does the temperature change in the tube wall? It is obviously a cylindrical system. So, the tube is cylindrical, and the second part is if R1 is 25 millimeters, R2 is 38 millimeters, what is the power required? What is the power required per unit length of the tube? And to maintain TS1 to be equals 150 degree centigrade and TS2 equals 25 degree centigrade, where the thermal conductivity is 10 watt per meter per Kelvin. So, the temperature at this point is TS1, at this point is TS2, TS1 is 150 degree centigrade, this is to be maintained at 150, the outside temperature is 25, the thermal conductivity is 10 watt per meter per Kelvin. So, how do you solve this? How do you find the temperature distribution in the tube wall? Now, when you see the tube wall, when you think of the system, that there is no heat which is being generated in the tube wall. The only thing that the tube wall experiences is some amount of heat is coming in at the inner surface, and it is going to get absorbed at the inner surface, then the same heat is going to flow through the tube to the other side. So, the radiant heater at the center provides the energy which is incident on the inner surface, gets absorbed, maintains the temperature, required temperature to cure the coating at 150 degree, then that heat has to travel through the solid of the tube, through the solid material of the tube, and go to the other side. So, this temperature is provided as 150, this temperature is provided at 25, the thermal conductivity is known to it, known in this case. Only thing you have to find out is what is the amount of heat that the heater must produce per unit length of the heater or per unit length of the tube in order to maintain the condition. So, any such problem should start with identifying what is the boundary, what is the governing equation and what are the boundary conditions. So, I am going to write the governing equation for the tube. When I am going to write the governing equation for the tube, it is going to be d2t by dr square plus q dot by k is equal to 0, but we realize that q dot is 0 in this case. No heat is generated in the wall, heat is absorbed at the inner surface, but nothing is generated in it. So, therefore, the equation, the governing equation for this case would simply be the governing equation for cylindrical system. It is a cylindrical system, d dr of r dt dr is 0. So, this is the governing equation. What you need to appreciate, identify is that I did not add any heat generation, because no heat is generated in here, heat is absorbed in here, heat is absorbed in one of the boundaries. So, it should come as a boundary condition, not in the governing equation. That is the only, that is the point which I think you should be very clear, you should have no questions about this, is that if it is everywhere in the tube, I would add it as a source term. Since it is only at the boundary, I am going to use it as a boundary condition. So, what my boundary conditions are? That q double prime, the heat flux, is equal to q1 double prime which is this known one, Q1 double prime at small r equals R1, which is at this location. So, this can then be expressed as minus k dt dr at r equals R1 is Q1 double prime. This is your boundary condition 1. This is your boundary condition 1. And what is the boundary condition 2? BC2. The boundary condition 2 simply tells you that the temperature at the other end of the surface is known to you, that is T is equal to Ts2 at R is equal to R2. So, this is my second boundary condition, which gives me what is the temperature at this point. When you solve this, you should get T minus Ts2 as Q1 double prime R1 by K ln R2 by R as the temperature temperature difference, sorry, Ts1. So, this is the temperature profile which you would get. So, this is T, which is a function of R. So, if I at R equals R1, this expression then becomes T S1, because at R equals R1, T is Ts1 minus Ts2 as Q1 double prime R1 by K ln R2 by R1. So, this is your solution of temperature profile, this part. Okay. And in here I identify that T is Tr. So, at R equals R1, Tr becomes equal to Ts1 minus Ts2, this part will remain unchanged except R is going to be equal to R1. All quantities in here are known except Q1 double prime. So, this equation would provide you a value of Q1 double prime to be equal, Q1 double prime is the flux. So, I have to find out what is the power required per unit length. So, power required per unit length would be twice pi R1 Q1 double prime, and the numerical value would be 18.76 kilowatt per meter. So, this is the value that you should get in this is the value you should get for by working out the value of Q1 double prime. Q1 double prime is the flux, but you are asked to calculate what is the power required per unit length. So, that is why you multiply it with twice pi R1, and therefore, you get this to be the value of heat to be supplied, power to be supplied per unit length of the tube. So, what we have done in this tutorial class is I have solved 3 problems. The first problem is heat generation in the wall, then convection at the other end. The second problem is heat which is absorbed in a wall which creates the volumetric which results in variation of the volumetric heat generation in the system. So, the volumetric heat generation is not a constant, but it is a function of position. So, that is the second problem which you have done. And the third one is a cylindrical system in which a heater is supplying energy to the inside of a tube to maintain the surface at a constant temperature. So, when we are writing the energy equation, when we are writing the diffusion equation for the tube wall, since no heat is generated, it is simply going to be the conduction term in the r direction to be equal to 0. Work it out and find out what is the heat to be supplied per unit length of the heater. So, these 3 I would request you to solve these 3 on their own, check if you are getting the same answer, and if you have any queries, interact with the TAs to this course, and I will supply you additional problems for you to practice on.